Okay, we're on to the final question of the paper. So, powerful winds are going to move ice particles and tiny water droplets. Okay, and the bottom of the clouds become negatively charged, the top become positively charged. And it says, give a reason how they're going to become charged. And just like absolutely everything to do with electrostatics, is this idea of friction, okay, which is going to knock off electrons off one thing and transfer them onto another thing. And I'll be honest, I don't know whether it's the tiny water droplets that end up with more electrons, or whether it's the ice particles that end up with more electrons. I'm just not sure about that. But yeah, it's friction between those two things that leads to an imbalance of charge within the cloud. Right, so here we've got our cloud like this, and the bottom of the cloud is negatively charged. Is that what he said? I think so. Yep. And the top obviously has got to have an equal amount of charge but opposite sign. Okay, I think that's enough positive signs. And then underneath we've got the ground, and initially the ground would have been neutrally charged, which means that we'd have had the same amount of positive charges and negative charges. But if you look here, now we've got a really big negative charge. So what do you think that's going to do to all of the electrons in the ground? It's going to repel these electrons further away, and now the only thing that you're going to have left, whoops, I've rubbed my ground out. Okay, the only thing that you're going to have left is you can have these positive charges remaining in the ground. Okay, so that's why the ground becomes positively charged underneath the cloud, is because the negative charges on the bottom of the cloud repel away the electrons in the ground, okay, and that just leaves these positive charges behind. Okay, now we've got this huge imbalance of charge. Okay, the buildup of charge in the ground causes the air to ionize. So when this imbalance of charges becomes large enough, then the air is going to ionize, become a conductor. Okay, and we're going to get a lightning strike. And this gives us some information about the lightning strike. Okay, it's going to be 32 kiloamps. And how many meters in a kilometre? There's 1,000. So how many amps in a kiloamp? There's going to be 1,000, so that's 32,000 amps. And then the other piece of information that we've been given is the charge, which is 15 coulombs. And it's asking us to work out the time. So that's the question mark. So if the exams are difficult, don't give up, don't quit. See what I did there? Okay, and it's up to you. You can substitute and then rearrange, or you can rearrange first and then substitute. I'm going to do it that way. Okay, so that means that the time is going to be 15 divided by 32,000. Okay, and that's going to get us 0.00047 seconds. Okay, double check. Two significant figures there, two significant figures there. It looks all good. But I don't like this way of expressing it, right? Because it's difficult for examiners to read. I think it's much more sensible to express that in standard form. So if you've done this on a calculator, your calculator should say 4.7 times 10 to the minus 4 seconds. Okay? Or you could express it in milliseconds. Okay, that would be 0.447 milliseconds. And that's the end of the paper.